Hello dear students, my name is Brajesh Chaudhary and you're watching the Quantum Guru. Have you ever wondered that when we jump into water or into swimming pool, we suddenly feel lighter? The underlying principle is the Archimedes Principle and a related term is a buoyant force. So let's first theoretically understand what buoyant force is, and then I'll demonstrate practically to explain the Archimedes Principle. So we have a container in which there is a liquid is there. Liquid has a density rho. The container is static, so any part of this container, every part of this container is equilibrium. So we have taken an imaginary volume V bonded by a closed surface S of the liquid. Because this whole setup is in equilibrium, so this imaginary volume is also in equilibrium. So now I want to make the free body diagram of this imaginary volume V bonded by this closed surface S. So actually that is nothing but that liquid itself, but we have made an imaginary boundary. So it has a its weight is acting. The weight is the rho into V. The volume is V, density is rho, so the weight is rho Vg. And this surface, this imaginary surface, is surrounded by the rest of the liquid, and by virtue of the pressure, it is the exerting a force due to pressure at all the points of the surface. And we know that the pressure increases as we go down, so the pressure at the bottom is more compared to the pressure at the top. And because this thing is in equilibrium, so the net force must be zero. So there is one the force due to pressure, and I want to replace the vector sum of all these forces at just one forces, and that's what we term as the buoyant force. So buoyant force is nothing but when a solid is partially or fully submerged in a liquid, the vector sum of all the forces by fluid on the solid is the buoyant force. Now because this is an equilibrium, and there are only two forces, one is the weight and other is that buoyant force, and their sum has to be zero, so that they must be equal and opposite. So because weight acts vertically downwards, so buoyant force must act vertically upwards. So that's why it is also called an upthrust. So buoyant force is also called upthrust. And the value of this buoyant force will be rho Vg. Here rho is the density of the liquid and V is the volume of that imaginary surface. And now suppose we have the same container, same liquid, and the same outer surface, but within that same surface there is some solid inside it. Here that was a part of that whole setup, and we had taken an imaginary surface. Now we have a solid who has the same volume as this and the same boundary as this. So now I don't want to know I am interested in the force exerted by this liquid on the solid by virtue of pressure. So again I have shown the force by the red color, and the question is that this force, the vector sum of this force was Fb. So the vector sum of this force, that is Fb. So this Fb and this Fb should be same or different? Actually they should be same, because this force due to pressure is has nothing to do what is inside. This has only to do with the liquid. Liquid has the same liquid density, and so whatever is pressure here, that would be pressure here, whatever is pressure here, that would be pressure here, and the boundary is the same, liquid is the same, so all these forces are same. So here the vector sum of all these forces must be Fb. So that is the buoyant force, and this buoyant force in the previous example, in this case we had written that this was a rho Vg. And what is rho Vg? When we have put the solid inside the liquid, so it has displaced the V volume of the liquid to occupy this position. So V rho G is nothing but the weight of the liquid displaced. So this buoyant force that we are writing is nothing but the weight of the liquid displaced. And now let's see a more mathematical method to get the same result. Now here in this case I have put a symmetrical body. It could be a cylinder or a cuboid. It has a cross section area A, and it has a height h, and at this level the pressure is P1, at this level pressure is P2. So we are only interested in the by-wind force, which is nothing but the vector sum of all forces from all around the fluid. So at the top pressure is P1, here the pressure is P2, and we know the pressure is more at the bottom, so the pressure difference will be P2 minus P1 will be just rho GH, and the pressure at top is P1, pressure at P1A, and force due to pressure at top is P1A, force due to pressure at the bottom is P2A. So the net force will be, the horizontal force will balance, so the net force will be the F2 minus F1, and that would be P2 minus P1 into A, and P2 minus P1 is nothing but rho GH and multiply by this A, so that will be again rho Vg. H into A is the volume of the solid, and the solid is totally inside the liquid. So we can say that whenever a solid is inside the liquid, partially or fully, I've shown the case of the solid fully inside, but that can also be true when the solid is only partially inside. So when the solid is partially or fully inside a liquid, so it is surrounded by liquid from all sides, and by virtue of pressure an upward force acts into the solid, and that upward force is called the by-wind force or upthrust, and this force is nothing but equal to the weight of the liquid displaced, and that's what the Archimedes principle. Now let's experimentally verify the Archimedes principle. Let me quickly explain the setup that I'm using. I have a weighing balance, I have a spring balance at stand. This is a Eureka jar, this is the empty container, this is the main weight. So what I will do, I will first measure the weight of this block A in air. So it will equilibrium, so this weight will be equal to the reading of the spring balance, so let that reading be W1, so W1 will be mg, so W1 is the weight in air. Now then I will put this block in the Eureka can. So when it will go into the Eureka can, it will displace the water, and the reading will also change because of the by-wind force. Now suppose the reading has become W2, so in equilibrium Fp plus W2 will become mg, and can put the value of mg again as W1. So what we will get, that Fb is equal to W1 minus W2. So by-wind force will be the weight in air minus the weight in the liquid. So we can measure the value of by-wind force by the measuring weight first in air, then measuring weight in the liquid. So by-wind force can be obtained, and we will also measure the weight of the displaced liquid. First we will measure the weight of this empty container, and then when it will displace liquid, so we'll measure the weight of the displaced liquid plus can, and if we difference their weight, we'll get the weight of the displaced liquid. So if the Archimedes principle is true, so we should get this Fb is equal to the weight of the liquid displaced. It means the W1 minus W2 should be equal to the weight of the liquid displaced, and that's what we are going to verify. So first of all, let me measure the weight of this block A in air first by this spring balance, and this weight is coming to be 427 gram weight. And I will also measure this weight by this spring balance, and let's see what weight we are getting here. And the weight that we are getting right now is 430 gram weight. The least count of this spring balance is a 10 gram, so we'll have a maximum error by 10 gram by the the reading of this spring balance. So but I will still go with the reading of this spring balance because I have to measure the weight of this block in air using this spring balance. So the weight of this block in air, block A in air, is this is a 430 gram weight. So before putting this block into liquid, let me fill this completely with liquid up to the nozzle level. And meanwhile I can adjust the level for our experiment. experiment. Okay, so that's almost there. Now this container is totally empty and the water is at the level of this nozzle, and I will now gradually lower this block into the liquid, and you can see that the reading is getting decreased as the block is getting inside it. And we can do one more action. If I go take it outside, the reading increases. The reading increases as it goes outside, and when it goes inside, the reading decreases. Now this is totally inside this container, inside the liquid. The reading has decreased to, this is exactly now 1.5 into 100 means 150 gram weight. The reading of this spring balance is now 150 gram weight, so that is W2. So the weight of A in liquid, W2 liquid, is 150 gram weight. So while this water is settling here, so we can calculate the by-one force, which is the W1 minus W2. So by-one force is 430 minus 150, so that would be 280 gram weight. Now let me measure the weight of this container plus displaced water. So this weight that I've got is 336 gram weight. This is the weight of the container and displaced liquid. So that is a, once again, this is a 336. So 336 gram weight. But had I measured this, okay, I hadn't measured this dry weight. I can measure it later also. First of all, this is a 336 gram weight, so I also need the dry weight of this container. So now what I can do, I should have done that earlier, but still no problem. I can put it all the water back here, and the dry weight of this container is 61 gram weight. So the dry weight of the container is 61 gram weight. So the weight of the displaced liquid is 336 minus 61, and that will be 6 minus 1. 336 minus 61, that is 5 and 7, 2. So this is 275. So to a very close degree we have verified the Archimedes principle. And remember, there is always some error in the experiment because of the limitation of the instrument that we are using. The least count of this instrument is 10 gram, and the error is not more than 10 gram. So we have experimentally verified Archimedes principle, and what we have shown that the by-one force, that is the weight of the solid in air minus the weight of the solid in liquid, is equal to the weight of the liquid displaced.